Hello, I'm Xinyun Chen. This is the recording of the second exam preparation section. And as always, if you have any more questions about any problems we discussed in this section, or if you have any other course-related questions, feel free to come to my office hours. It is 3 to 5 p.m. every Thursday. So let's get started with the questions. So for this exam preparation section, we have two questions, and both of them are related to search algorithms and heuristics. Recall that for the last exam preparation section, we mainly discussed the key procedure of DFS, BFS, and uniform cost search algorithms. So this time we will kind of have a brief recap of DFS and BFS, and then we will start to focus on A-star search, which is the main new thing we learned this week. Okay, so let's start with the first question. So this question is called a rubric search. So the problem description is pretty long, but we don't really need to understand the full details to work on this question. The main thing is that we need to know some key numbers related to the formulation of this search problem. So let's take a look at the problem description. So the first sentence says that a Rubik's cube has about 4.3 times 10 to the power of 19 possible configurations. So effectively, this number means basically it is the number of possible states for a search problem. Then the second sentence says that any configuration can be solved in 20 moves or less. So basically, this sentence is further explained in the last sentence of this paragraph. It says that any configuration can be solved in 20 moves or less. So basically, it means that for the optimal solution, we can it is always not greater than 20. Then the third thing we need to understand is that the branching factor is 27. So it means that starting from each node in the search tree or graph, there are at most 27 other nodes that are directly connected to this node. So basically, this number is at most 27. So based on this information, we can kind of understand what are for all the possible choices of these sub-questions, where are these numbers come from. So basically here, 20 just means the optimal move. So for this specific question, it says that we assume our best solution is exactly 20. So basically 20 just means that if when we do the search, if we only search for one path and it happens to be the optimal path, then basically in this configuration, our final answer is we only need to expand 20 states to get to our final answer. Then for the second number, 4.3 times 10 to the power of 19, as we marked before, this is just all the number of possible states. So basically we can think about this number in this way. So let's say if we are doing a graph search, so recall that last time we discussed that for graph search, we will never expand one state more than once. So basically when we conduct the graph search and we exactly visit each state once, then the answer should be four times this number about 10 to the power of 19. Then the source of the third choice, 27 to the power of 20. basically it means that because we previously we said that the branching factor is 27. So effectively it means that at each search step we will expand all the 27 possible moves. Then we explore this like full search tree for 20 steps, because we know that the final answer should be like less equal or less than 20 moves. Then but from a note in the problem statement, it says that this number is much larger than the number of possible states, because we know that for the Rubik's problem, actually as noted in the first paragraph, the state space graph does contain cycles. Therefore, if we in this case, if we don't mark all the states the search has visited, then the search could go into an infinite loop. Therefore, this is why the 27 to the power of 20 is much larger than the number of states, because some nodes may be visited more than once in this search tree. Okay, so after understanding these numbers, it will be relatively easy to solve the concrete questions. Then let's go through them one by one. Let's take a look at the DFS tree search first. So for DFS, recall that basically it just means that for each search procedure, we will go down one path to the end, like until there's no nodes that we can visit it anymore. Then we go backtrack. Then we can explore the next path. So basically, in this, for the best case of DFS tree search, it kind of means that let's say when if the first path we explore happens to be the optimal solution, then it means that we only need to visit exactly 20 states in this search. So it means that for DFS tree search, the best case is only takes like 20 moves. Okay, then what's the worst case? Recall that for a DFS tree search, it doesn't like mark the states that the search has visited, and also it may it only explore other paths until the current search could not continue along the path. Therefore, and also in our search problem, it contains cycles. So this means that when we do a DFS tree search, in the worst case, it will never finish when it goes into an infinite loop in this search tree. Then for the DFS graph search, again, in the best case, our result is 20, because we only need to explore one optimal path. But this time, for the worst case, the number of states expanded will just be the number of states in this search problem, because for graph search we will only explore each state once, and so this is the worst thing that will happen in DFS graph search. Okay, then let's see what are the results for BFS. For BFS, recall that how it does search is that for each state, it will expand all the states that is like one step after the start node, and after it explores all the states, it will continue to explore the nodes in the next level. So basically, it will only proceed to the next level after it finishes exploring all the states in the current level. So in this case, basically it means that even if the optimal solution is 20, it will always explore all the other options in the previous levels before the search could explore any node in the current level. So and here we do a graph search. So it basically means that the results will be not worse than the number of states. But due to the design of BFS, for both the best and the worst cases, it will just explore all the possible states, because we know that the optimal solution in our case is exactly 20, and 20 is like is an upper bound of the optimal solution for all the starting states. So this becomes our final answer. Third, let's take a look at the results for the A-star search. So basically, for all of the search algorithms we discussed in our previous exam preparations, like the DFS, BFS, and uniform cost search, basically at each search state, its cost only considers like all the accumulated cost from the start node to the current node, but it never considers the cost to the goal node. So basically this is the reason why when we so basically at a certain level, when there are multiple nodes that are equally good based on the costs from the start to the current node, then the search kind of cannot distinguish among them, and it could only randomly or alphabetically choose one node to proceed. However, for the A-star search, basically for each node, besides the cost from the start to the current node, we will also have a heuristic called usually called H, which is the approximated cost from the current node to the goal node. Then by adding them together, we can have an estimate of the cost if we expand the current node. And so if the heuristic is kind of like if this approximated heuristic is close to the optimum heuristic, or if it can kind of well distinguish among different nodes with similar F at this point, then this A-star search will be much more effective than the BFS or the uniform cost search or the DFS. Okay, so with with all this discussion, we can take a look at these problems related to A-star. So suppose for A-stars we have a perfect heuristic. So perfect just means that at each node we already know exactly what's the optimal cost from the current node to the goal. Then in this case our results will be 20, because basically it from this heuristic we can already know what's the best node we need to expand at each step. So this is the best. Then the second thing is that when we have A-star research with a bad heuristic, Hn equal to 20 minus H star n. So what does this heuristic indicate? So we know that H star is the perfect heuristic. Then when we when we have 20 minus H star n, it basically means that at each step the search will kind of expand the worst node first, then the second worst node, and the best node will be expanded after all these worst nodes are expanded. Then and also notice that here we are doing a tree search. Then basically it means that in the worst case we will expand 27 to the power of 20 nodes, because we know that the branching factor is 27, and there are 20 moves to go from the start to the goal node. But basically it is a tree search, but then why the answer is not infinity? Because we know that for this like Rubik's search algorithm, each time when we like explore like one more step in the search, the cost will also be added once. Like noted in the first paragraph, each edge has cost 1. So it means that we will not even if like the search goes into a loop, we will not consider like any loops that is like longer than like 20, because it will not be the it will definitely not be better than the previous nodes, and the A-star tree search will definitely explore a better solution before it reaches another loop. So in this and also and actually the yeah, so basically this is kind of explanation why for A-star tree search still we can guarantee that the search will terminate. Also, we will have to explore a much larger number of states than needed. Now let's see how the solutions may be different for A-star graph search. So firstly, the best case is also like 20. Basically, we just need to explore the optimal solution in the search. By this time, because we have graph search, so we will not like explore once a state more than once. So this time, our best result becomes 4 times 3, 4.3 times 10 to the power of 19. Which is the number of possible states for this search problem. Okay, so that was the first question. Then for the second question, we are mainly like interested in learning more about like the different properties of the A-star heuristics. So like let's take a look at the general problem statement first. So this time we consider a connected undirected graph. Again, start from S to the goal node G, and we consider that the edge weight is always positive. So but basically it means that when we design the heuristics, definitely it will be like no less than 0, or otherwise it is not it is kind of non it will never be a good heuristic, because we can just set the heuristic to be 0. And we define H star as the basically the best heuristic we can get. So for the part A, we want to study like the properties of admissible heuristics. And we are doing A-star tree search. So basically H is the admissible heuristic, and H prime is another heuristic we are going to ask in sub questions. Then we know that C is the cost of this path formed by H prime. Then before we go into like the details of the subprograms, let's review some key definitions and properties of admissible heuristic first. So from the course, we know that by admissible heuristics, we mean that this heuristic should be like always no greater than the optimal heuristics we can get. So it means that H is always like not greater than H star. And with the A-star tree search, an important like property is that A-star tree search with admissible heuristics is optimal. So basically, it means that for this specific question, it means that if we can prove that both H and H star are admissible, then basically it means that the path C basically has the optimal cost for both of these for both of these heuristics when they are used in A-star tree search. Okay, then let's see these subprograms. So firstly, we want to see when we have these new H primes, whether they are still admissible heuristics. For the first one, when H prime is half of the H, this answer may be pretty easy to understand, because we know that when it is half of H, it is no greater than H, and also we know that H is no greater than H star, so it means that this H prime is still an admissible heuristic. Similarly, because we know that H is always no greater than H star, so when the H prime is the average of H and H star, we know that it will also guaranteed to be no greater than H star. Then for the third subproblem, since H prime is non-negative number plus H star, so basically with this new heuristic, we only know that H prime will be not smaller than H star, but definitely when H is greater than 0, then this means that H prime becomes not admissible anymore. So basically, for the answers here, the answer for the first subproblem is that C is equal to H star, and similarly for the second subpart. Then for the third subpart, the answer is that C is greater or equal to H star. Notice that for C greater than H star, this answer will never be selected, because in a graph, when there is only one path from the start to the goal, then no matter what heuristic we use, we will because there's only one path, so it is so the path we found is still the optimum path. Then let's take a look at the parts from 4 to 6. So for all of these three subprograms, they share a new definition called the KX. Basically, it defines all the basically K includes all the neighbor nodes Y, which has smaller heuristics than the X node. So basically, it kind of this definition is related to the optimum heuristic H star. Then with this definition, we want to see whether H primes are still admissible heuristics. So the part 6 is easier to understand, because we know that H is an admissible heuristic, and because here H prime takes the minimum of a set of H heuristics with the HX. So basically, it means that H prime will always be no greater than HX, because it takes the minimum of amount including this SHX. So definitely for 6, the answer is still the cost is equal to the H star of S. Then for the part 4 and 5, we know that when the set K is empty, then again we can know that H prime is no greater than H. So in this sense, such kind of nodes satisfy the condition of admissible that we need. But when the set K is not empty, it may not be that straightforward to know whether H prime still satisfies the criteria of admissible heuristics. Then let's do some derivation to see why like H prime is still an admissible heuristics in both with the conditions of either 4 or 5. Okay, let's get started with the part 4 first. And let's see that when kx is not equal to empty, why this condition still leads to the conclusion that H prime is no greater than H, and thus H prime is still an admissible heuristic. So we can prove this by induction. So first, we sort all nodes such that x when x, so basically for h star hi is greater than h star xj when I is when I is greater than j. So for example, we know that for the goal node h star g is equal to 0. So definitely at least we know that x0 will be g, and etc. And we know that for hx, and we know that basically for when x equal to g, basically h prime g will equal to hg, because for like in the case of g, we know that kg will be empty, right? Because there will not be like any heuristics that is even like smaller than the goal node. Then let's suppose for the current I, so for the current I, and for all j smaller than I, all of h prime j is already no greater than xj. Then let's see that how is that h prime xi. By definition, it will be like h prime xj and because we already know that h prime xj is no greater than h for all the nodes that is that precedes to the xxi in this sorted list. So we basically know that h prime is also no greater than h when for xi. So by induction, it means that all the nodes satisfy this this in equation. So which effectively means that with the condition 4, C is equal to the optimal heuristic starting from the S node. Okay, then let's move on to see why with the heuristic in the subproblem 5, we again can show that H prime is an admissible heuristic. 5. So we know that for each x, there will always be a optimum path from x to g. So from the neighboring nodes k, we know that there exists a certain node y prime such that h star x is equal to h star y prime plus cos h y prime, which means that y prime is on the optimum path from x to the goal g. Then with this equation, we know that h prime x is no greater than h y star plus cos x y prime. And again, we use a similar way to prove by induction. And we assume that here for the y, we already know that it is an admissible heuristics. So basically, it means that it is not greater than h star. So because we already say that it is the optimal path, so basically it means that h prime is not greater than h star, which means that in the case of condition 5, still we know that h prime is an admissible heuristic. Okay, so after going through all these 6 heuristics in problem II, it is asking which heuristic is both admissible and dominant H. Here dominates means that H prime is greater than greater on always not smaller than h for all the possible nodes. So recall that when we try to show these heuristics are admissible, like for the first heuristic, we want to prove that h prime is always not greater than h. So definitely this is not the answer. And for for the third condition, it is already not admissible. So also this will not be the answer. Then for condition 4, we want to show that h prime is not greater than h, so it is not the answer. Then for condition 6, similarly, it is not greater than h, so not the answer. So basically, the remaining conditions are the second or the fifth. For the fifth, actually, in the next subproblem, we will show that h prime dominates h for the condition 5 only when the heuristic h is also consistent, and we will defer the discussion later. But for the condition 2, recall that earlier we said that because h is always not greater than h star. So basically, when we take the average between h and h star, definitely h prime will be basically not smaller than h. So this effectively means that for this question, our answer is true. Okay, let's move on to the part B. So part B is discussing about like the consistency of the heuristics. And also here we are studying the A-star graph search. Again, before we look into like the subproblems, we want to recall some like key definitions and properties of consistent heuristic and A-star graph search. So firstly, for a consistent heuristics, its definition is related to like the triangle inequality. Basically, it means that if we subtract the heuristics of two nodes, then this number should be like not greater than the cost between the weight of the edge between these two nodes. Yeah, because we know that if it is indeed greater than this cost, then basically it means that we will have another way to construct a better heuristics for like the for the at least for the node X. Then by the definition of consistent heuristic, it implies admissible, which means that only admissible heuristics could be consistent. But like consistent here. So basically, if a heuristic is already not admissible, then it cannot be consistent. But even if a heuristic is admissible, it also may not be consistent. And in the lecture, we also show that A-star graph search with consistent heuristics is optimal. So again, basically, when we like try to compute like the optimal solution using the heuristic edge, it is guaranteed to find the optimal path. Okay, so basically for this subproblem, we are asking so basically here the conditions are the same as the previous subpart, but this time we are asking whether H-plane are still consistent heuristics using like all these like different conditions. So firstly, similarly, we can show that H-plane is still consistent because like basically it is just where this difference is like divided by 2, so it is still like lower than the cost between the nodes X and Y. Similarly, we can show that the average of H and H star is also like still consistent. For the third heuristic, previously we showed that this heuristic is already like not admissible because it could be greater than H star. So basically here it is also not consistent. So basically the answers are like for the conditions 1 and 2, the optimal solutions don't change, and for the condition 3, the optimal the cost of the solution found by this search algorithm will be like greater or like equal to the H star. Now, before we go to like conditions 4 and 5, let's talk about the condition 6 first. So basically here, H-plane, it takes the minimum of the H value for among the node X itself and its neighbor nodes. So basically for its neighbor nodes, it means like all those like connecting nodes, so that their like optimal heuristic values are smaller than the current node X. Then earlier we showed that H-plane is still an admissible heuristic when H is admissible. But actually, when we take the mean among like all these neighbor nodes, this heuristic is no longer consistent because it kind of ignores intuitively. It kind of ignores the cost between the node X and its like neighbor nodes. So here is a pretty simple like counter example. So basically, node S, A, and B are fully connected, and there is an edge between B and G. So we know that let's say for the heuristic edge, HG is equal to 0, HB is 4, HA is 5, HS is 6. Actually, all of these are like optimal heuristics. But when we take the B, then H prime G is still 0. But this time H prime B also becomes 0 because it is directly connected to the goal node G. Then H prime, and both H prime, A and S take the H values of B. Then what's the problem here? We know that because there's already an edge of cost 1 between A and B, therefore by comparing H prime B and H prime A, it definitely does not satisfy the consistent criteria because the difference here 4 is greater than the edge cost 1 here. So like this is a counterexample to show that this heuristic is not consistent. And then when we use the graph search, and if the heuristic is not consistent, then the cost may also be higher than the optimal heuristic H star. Now let's again move to the conditions 4 and 5 and prove like why they are like still consistent heuristics. Now let's prove that for heuristics in part 4 and 5, why they are still consistent heuristics when H itself is a consistent heuristic. Let's start with the part 4 first. So basically in part 4, again, we focus on the case when K is not empty. Because when K is empty, then this proof is pretty straightforward. So basically, H prime X is not greater than H prime Y minus HY plus HX. And because H is a consistent heuristic, we know that this term is not greater than cos xy. So basically, H prime X is not greater than H prime Y plus cos xy. Therefore, H prime is still a consistent heuristic. Now let's move on to the part 5. First, we note that from the definition of H prime, we know that when K is not an empty set, there exists Y prime, so that H prime X is equal to H Y prime plus cos X Y prime. And again, because H is a consistent heuristic, this effectively means that Hy prime plus cos xy will be, this term will be not smaller than Hx. So effectively, it means that H prime X is always not smaller than Hx. So with this fact, we can prove that when we subtract H prime Y from H prime X, it is not greater than a certain h y plus cost y minus h prime y, and we know that this term is greater, the term h prime y is greater than hy. So basically this cost is also not greater than cost xy. Effectively, it means that h prime is also a consistent heuristic. From the previous discussion, we already kind of know the answers for all these problems. So basically, the heuristic 1 is still consistent, heuristic 2 is still consistent, 3 is not, 6 is not, and 4 and 5 are still consistent. Then for all the conditions above, which one satisfies h prime is consistent and also dominate h? From the discussions in the part A, we already know that 1, 3, 4, and 6 could not be the answers. Then the same as the part A, the heuristic h prime still dominates the heuristic h. So 2 should be selected. From our previous derivation for the condition 5, we know that h prime is always not smaller than h. So it means that 5 is also the answer. That's it. Thanks for watching this recording. And if you have any more questions, feel free to come to my office hours.